have to know that angle and that angle separately. Well, yeah. Yeah, I can talk to you later about that. I'm not sure if what I'm getting at here is what you were asking, but I'll talk to you later about that. Okay, thank you. We're ready. I'm good. I heard the music. Thank you. Okay. So what we're doing now is we're going to talk about linear and angular speed. How many of you go to the playground and get on the merry-go-round? Still. Every once in a while I will. Okay, good. Some of you do. That's good to see. Okay. Now, what happens when you're on a merry-go-round down in the park? And matter of fact, I would encourage you on a dry day, go down to one of the parks where there's one of those nice little merry-go-rounds, and don't scare the kids off or anything, but just get on the merry-go-round. Have a friend start it turning. Okay? Now, you go sit right in the very center of that. You sit in the very center of it, and what's going to happen as the thing rotates?
Push out.
No, you're sitting in the middle.
Yeah.
Nothing really happens when you're in the middle. You don't feel that much pull. Yeah, you're just in a circle.
Yeah, you're just sitting there rotating around in a circle, right? Yeah, all you're doing is rotating around in a circle, sitting right there in the middle. Okay? Now, you go out and get on the edge.
Then you get
Or say halfway out to the edge, and you hold on to one of the railings. Halfway out to the edge on a circle. Maybe I should draw a picture. So here's the merry-go-round. You're sitting in the middle, and this merry-go-round is spinning. And you're just going to be sitting there rotating if you're sitting in the middle. Now, if you go out here and hold onto a rail, and you sit out here, you're going to be moving around in a circle with that radius, aren't you? And how's that feel?
Feels like it's pulling you off.
It feels like you've got some forces on you when this thing's rotating, doesn't it? Feels like you got some force on you. And then also, let's say it's a calm day. Aren't you going to feel, even on a calm day, your hair blowing a little bit in the wind? Now, you come out here and sit out here, and how's that compare to sitting here?
More force.
There's more force on you, but what about your hair blowing, if you have hair? Okay. Okay. Right? What do you feel? More wind, don't you? Aren't you moving faster out here? Faster out here and slower in here. And in here, you're just almost stationary, right? Okay. Now, at the same time that you're feeling that speed, right? That's called linear speed that you're sensing out there. It's how fast you're moving out there. You're also, the merry-go-round is in rotation, isn't it? Okay, now how do you find rate? Rate. You've been doing this since you were a kid, and since beginning algebra. What's a famous formula that you all memorized?
Speed times distance or something.
Yeah. So rate equals distance over time. Or the way you oftentimes will see that is distance equals rate times time, right? Right? Distance equals rate times time. It should, thinking about the merry-go-round, is it should make sense to you that there is some connection between what's called the linear speed, what you're feeling when your hair's blowing, how fast you might be moving, and how fast the rotation is occurring. There should be some relationship there between the linear speed, how fast you're physically moving, and how fast the object you're on or the track you're going around is rotating, your rotational rate. Okay? So I just want you to have a sort of a gut sense of that. And like I said, on a dry weekend, go down and get on a merry-go-round with a friend and actually try this out a little bit. Okay. So let's now look at the math that makes that connection for us. It's pretty easy if you understand what we just did a little bit ago. Here we have a radius with a circular arc length and a central angle, just like we did. And the relationship between those three items is, we all memorized it, S equals R times theta. Okay, so the arc length equals R times theta. How do you measure theta?
Radians.
Thank you, radians. How many of you will forget that on a quiz? Half of you, okay. That's got to be radian measure or converted into radian measure. You'll hear me say that many times, and I'll scold you after a quiz or exam when you make that mistake. That's got to be radian measure. Okay. Now, how do we find rate again? We take a distance, divide that by time, don't we? So why don't we come back and just do something really simple here in basic algebra. S equals R theta. Why don't we divide both sides of this by time? It's not tough, is it? Divided by time. So we're going to get S over T equals R times theta over T. Now, what are we holding constant in circular motion?
The time.
No, not the time.
Distance.
Not the distance. What's left? The angle, not the radius. Okay. What are we doing? We're doing circular motion, aren't we? This is fun stuff. Okay, we're doing circular motion. Okay? Now, when I'm doing circular motion, time is changing. The length on the arc is changing. The angle is changing. What's not changing?
The radius.
Thank you. The radius. The radius is our constant. Okay. Feel good? Everybody feeling good?
Got it.
Okay, circular motion. Many of you are going to be taking some physics. Most of you, if not all, are going on beyond this class into calculus. You will do circular motion problems, and you'll have a jump start on most of the other people in the class if you remember this. When you're in circular motion, the radius is the thing that's constant. So what we have going on now is we have S divided by T equals holding R constant and theta divided by T. Okay. This is called linear speed. Distance divided by time, miles per hour, feet per second, kilometers per hour, meters per second. The sense that you feel with your hair blowing when you stick your head out the car window or on your bicycle. That's called linear speed. It's also called linear velocity. Feel good? Everybody got it? Okay. If that's called linear speed or linear velocity, and then over on this other side we have this radius, then what is theta over t? How would you refer to it? Rotational speed or angular speed. Make sense? Angular speed. So many degrees per second. So many radians per hour. So many revolutions per minute. Make sense to you? Angular speed. And what we do in math typically is we usually start with very simple fundamental relationships like we saw earlier, S equals R theta, and then we start getting fancier with it. We start adding more stuff into it to make it more complex, which allows us to understand and analyze things that are more complex. So we start with the understanding of arc length equals R times theta, and then we divide both sides by time, holding the radius constant, and we get this relationship that linear speed is equal to the radius times the angular speed. how do you have to measure the angles? In radian measure. In radian measure. Okay. Just like it comes from here, doesn't it? And we talked about that earlier. Okay. Now, we change the symbols. Instead of always writing it this way, for the linear speed equals radius times angular speed, we give this the symbol v, indicating linear velocity or linear speed. And over here, we're going to give you another Greek symbol. It's not called a W. It's kind of a curved looking W. It's called omega. And I forgot to give that to you the other day. Omega. And that's the symbol that's typically used in physics and engineering and in math textbooks. V equals R omega. Any questions?
Yeah, so the V equals speed over time.
What's that again?
The V equals what?
V is the same as arc length divided by time. Omega is angle, central angle in radian measure divided by time. Central angle in radian measure divided by time.
Does the V stand for velocity?
Yes.
Okay.
Okay. Good. Ready for an example? Okay. Observe, again, this is a linear relationship. This is a linear relationship. Okay. Now, look what would happen if we were back on our merry-go-round for just a second before we do an example. If we were in here, we would be moving at a certain speed, v, while the angle is changing at some rotational speed, omega. What if I said this was, say, 5 RPM, revolutions per minute? Omega is 5 revolutions per minute. Isn't that an angular speed, RPM, revolutions per minute? And one person's head's in the camera. Oh, there, they moved the camera, good. Okay, omega equals 5 revolutions per minute. Revolutions per minute. See it? Revolutions per minute. Okay, so there's the angular speed. Now you're on the merry-go-round and you're going to feel something, aren't you? If you're out there at that distance. What if you were out here further? How fast are you going, faster or slower?
Faster.
Yeah, the rotational speed's still 5 revolutions per minute, but you're going to be traveling some faster value, aren't you? Make sense? Yes. And notice this relationship right here. If you held the omega constant, if you held the angular speed constant, like I have here, 5 revolutions per minute, and I move at different move out to a different radius, I'm going to be increasing this speed linearly, aren't I?
Yep.
Yeah. This is just, again, like y equals mx. If I held the omega constant and let this vary, then what that indicates is we're going to actually see a linear distribution of velocity as you move away from the center. A linear distribution of the velocity v as you move away from the center. Okay. Let's do an example. How many pieces of the puzzle do I have to give you for you to be able to solve for something?
2.
2 out of the 3, right?
Yeah.
Okay, good. So let's build an example. Now, do you agree that it's going to be kind of boring if I tell you 5 revolutions per minute here and give you a radius and have you tell me the speed? That'd be almost like the last question the arc length problem we did, right? So why don't we do something a little different this time? Let's go ahead and use 5 revolutions per minute here, but let me give you the speed, and let's figure out what radius we would have to have. We have to get two of the three items to be able to make a problem out of it. Okay, so here's an example of circular motion. We have a velocity of, say, 20 feet per second, 20 feet per second, and we have an angular speed of 5 RPMs. What I'm interested in knowing is what radius do we have in inches? What radius would we have to have beyond? What radius would we have to be on in inches to be able to determine to fit this information? All right? Okay. Again, and I'm trying to emphasize last session and then earlier today with examples, is always draw a picture if you can, please. So we are out here on the edge of the wheel. This wheel, or the thing, is rotating at 5 revolutions per minute, and that's the omega reading, kind of a curved W in shape. And we have a 20 feet per second velocity on the edge. What we're trying to figure out is the missing piece of the puzzle here. What radius do we need? So there's a picture with the given information. Here's a summary of the data and what we're looking for. And now we're going to work up the problem. So we write V equals R omega. We drop in the given information. We know this piece over here is 20 feet per second. It's got to be equal to our R times our omega. And our value we don't know. The omega is 5 revolutions per minute.
Do we have to do unit conversions to get the answer?
I hope so.
Yes.
Yeah, I think see, when you write this stuff down, you can see that you got a mess here, right?
Yeah.
We have a mess. So what we need to do, obviously, is get these units to become consistent. Okay. So we can tag on. I like the fact that you asked that. We know that this omega has to be in radian measure. So we know there are 2 pi radians in 1 revolution. So now the revolution units will disappear. And that gets that turned into radians, which is what we needed. Notice our left side of the equation over here has seconds in it, and the right side has minutes in it, in the denominators. So we better get those consistent also. You could go to either side, couldn't you, to make this conversion? Either side. And why don't I come over on the left side, and I know there are 60 seconds in 1 minute. And so now my second units on the left side here disappear, reduce out. And now notice I have both sides, I have division by minutes, don't I? Couldn't I multiply both sides by 1 minute? And that maintains the balance in the equation if I multiplied both sides by unit, 1 minute in units. Right? So technically in the math, if you ever see a common unit, like in the denominator, by multiplying both sides by that unit, minutes, you can reduce this out. Right? Is everybody comfortable with that, doing that? Multiply both sides by minute units, so they disappear. Let's see. We want inches, don't we, of radius. So we know in 1 foot there are 12 inches. So over here on the left side, I know that I could tag in a 12 inches in 1 foot, and my feet units disappear. And now I've got the correct units I need here, don't I? Okay. So let me tidy up. I'm going to erase the picture. Let's tidy up the numbers here a little bit. We have 12 times 60 times 20, and now the units on the left side over there are purely inches. And over on the right side, we have our unknown r, and we have to multiply that by 10 pi radians, right? Everything okay? Feel good? It's not complicated if you write the steps down. You will mess it up if you don't write the steps down, guaranteed. Okay. So now, how do we find r?
Do math.
We divide both
10 pi
sides.
radians.
Divide both sides by 10 pi radians, don't we?
Yeah.
Divide both sides by 10 pi radians. And over on the right side, the radian units disappear. The 10 pi reduces out as well. And we're left with our result for r being equal to the number you see here, which is going to be,
I got 4,523.9.
okay, r is approximately equal to, you said 4,000.
523.9.
0.9 inches. And that's per radian, right? Isn't the radius equivalent to the arc, the radius on the arc, right? Isn't the radius a length per radian effectively in what we talked about earlier? Okay. Now,
So right now.
I want to
we're-
check, I want to make sure that this value feels right first, but let me answer your question first, Dale.
Right now, do we need to be in radians on our calculators?
There is nothing requiring that to have to be that way. All you're really doing here is punching numbers, aren't you?
Well, then I got the same thing as she did.
Right here?
Yeah.
Okay.
Yeah, I didn't get that.
He didn't get that. Okay. Now, how can we tell who's right? Is he right, or are those other two people right? So watch. This is what I always want you to do with your calculator, or with your brain first, is I want you to look up here at the math and eyeball this. Doesn't 10 go into 20 twice? And don't you have 120 times 12 here?
Yeah.
Right? And then it's all divided by pi. So aren't we going to be getting 144 with a 0 tagged on? Divided by pi?
Yeah. That's right.
Does this answer feel right? Looking at this? Does this answer down here feel right looking at this? No. See, I would eyeball this. This is roughly a third, isn't it, of roughly 1,500? So shouldn't this be something less than 500 here? Okay, so let me go punch this mess on the calculator and see if we have some error somewhere. So back over to the calculator. We have, I'm just going to take the original form of it, 12 times our 60 times 20. And we're going to divide that by 10 pi, aren't we? Parentheses 10 pi. Anybody have an idea what the mistake was people made before? Is they, the other people, the couple people that mispunched this, they did the following like this. This last one is wrong. What happens is the calculator interprets this as this product divided by 10. It takes that result times pi. That's wrong.
Even when you press enter and get the answer from 12 times 60 times 20?
No, that's going to be fine.
Because when I pushed,
if you do it,
when I got the answer and then divided the answer by 10 pi, I got 4523.892.
Okay, so you have to be careful. Notice what I did up here at the top. This is the correct way to do this. When you see a cluster of calculations in a denominator, make sure you put that in parentheses. Otherwise, it's very common to make an error. A cluster of items in a denominator or a numerator, typically, if there was addition or subtraction in this numerator, you'd need parentheses up there as well. Everybody hear that? That's important. Notice how, come back to the board. So this is 452.439. Here's the correct answer right here, approximately. And here's an exact answer in inches right there.
458.
Oh, I'm sorry. I don't know where's it.
450.
Oh, interesting. 458.37, right? Now, I'm not going to take the time right now because of the recording process, but there's something fishy there. I'm surprised those aren't exactly the same digits except a decimal place shift because of the 10 there. I'm not sure what went on, but I'll have to think about that. Let's not worry about it. It's not too important. Just remember what I said about using the calculator. And more importantly, use your brain first. Use your brain first to have a sense of the kind of answer you should get. Now, if you took this answer and divided it by 12, it would convert it into feet, would it not? If you divide this answer by 12, it would convert it back to feet. Okay, and that might be a more appropriate thing instead of thinking of this in terms of that large number of inches. So if we took this answer back here previously and divided this by 12, we would see we need about a 38-foot radius roughly. This is about 38.2 feet for the radius. So what we would have to do then is we're in circular motion and we'd have to be out here about 38.2 feet to be, and we're moving at 20 feet per second with a rotational rate of 5 revolutions per minute.
It's always counterclockwise for positive.
For positive, yeah. But, you know, you could be spinning the other direction here. Now let me show you real quickly. We have a few minutes left. Actually, I think I'll wait until maybe the next session because I'm sure you'll have some questions about this circular motion. But you can start talking about bicycle gears or a motorcycle or a car or a CD player. Anything that is spinning in circular motion are the parts in a sewing machine. Your chain wheel on a bicycle, up front where your pedals are. Larger radius, and then you got your chain that connects back to your gear cluster on the back. It's usually smaller radius. There's a relationship between that pedaling rate and how fast your bike or might be moving down the road. Doesn't that make sense? And there's a connection, and the connection is simply through ratios of V equals R omega. It's that simple. Okay. Let's talk a little bit. Let's go ahead and go to the last segment, or actually segment 3. And then we're actually going to tie probably segment 3 and segment 4 together today. So we'll give them a second to go ahead and queue up for the next